Okay. So I want to recap a little bit about weak entities and specifically why we use them versus could we maybe draw an ER diagram a different way without using weak entities. So just recap quickly, weak entity is an entity that can't be uniquely identified by its own attributes. So it pulled in a key from somewhere else, from a supporting entity. The combination of one of its own plus some other attribute makes its key. So here's how we draw them, and here's the example we used. Was a class is like an instance of a course, and a class has a partial key. So semester is a partial key, but that's obviously not enough to uniquely identify it, because there are lots of classes in any given semesters, classes of a different course. Okay. So we draw it with a double rectangle and a double diamond. things here. I didn't give the entities or relationships names. I just made up some keys and partial keys. A strong entity over on the left with an actual key, A. And then a weak entity with a partial key, B, is supported by whatever that strong entity is. And then some other weak entity is supported by that weak entity, which means everything on this chain at some point only exists in the sense of the strong entity at the end of it. Okay? And so now, what do we do about keys here? So what is the key for the weak entity on the very far right of this chain? Well, it just works the same way. You take your partial key and you combine it with the key of the supporting entity. So the thing in the middle, its partial key is B, we combine it with the strong entity key A. And then that whole thing, B, comma A, is the key of the middle one, so we combine that with the partial key C on the far right. Okay? Yep.
So when we turn this into like a table, will this be all in one relation? Or?
So when you turn this into a table, would it all be one relation? Each of these weak entity sets would become a relation. The diamonds, though, the supporting relationships, get merged into the weak entity sets, since it's one to many. So if we turn this into tables, we will have 3 tables total.
Can you ever have double diamond without a weak entity set?
You have a double diamond without a weak entity set? No.
So entities can only connect to each other through a relation set, right? They can't connect to each other directly.
So can these only connect to each other through a relationship set? Yes. You can't draw a line straight from an entity set to an entity set. Yeah, it always goes through a diamond. So there's maybe a concern here. These keys just get progressively more complicated the longer this chain becomes. And you end up with some compound key with like 3 or 4, 10 parts to it, if it's a really long chain. And so that might be setting off some alarms for you, but as far as the ER diagram goes, it doesn't matter. We don't care. This is the ER diagram. These braces I've drawn down here on the bottom, those are not part of the ER diagram. We don't need to show that this key gets more and more complex in the ER diagram. So just draw it that way. It doesn't care about this potential issue. Now, why is this a potential issue, and why should it be raising alarms? Because primary keys should be small. They should be simple. I've said that before. And it really comes down to because a primary key is used in a lot of places, so it's going to get copied a lot. So what this would look like after translating to schema would be, we have like the one on the far right really does have a primary key of 3 different things. So that is potentially a problem that we can fix, but for now, let's just get the ER diagram right, and then we'll refine the schema and the keys later. It turns out there is a way we can address this problem. So we'll talk about that later. It's important to get the understanding of a weak entity set just in terms of the ER diagram first. And as a hint, so classes and courses, how many of you looked at the LMS, the project phase 1? Okay, not as many as should have, but we're making an LMS, a Canvas-like system. There are classes and courses in an LMS, so hint, there are probably some weak entities in your LMS diagram. Yeah.
So the dashed underline means partial key, right?
Dashed underline means partial key.
So every weak entity set has to define partial key, and then the key which they define comes to the primary key.
So every weak entity set has to define a partial key, and it has to be connected to a supporting relationship. And somewhere at the end of some chain of supporting relationships, there has to be a strong end with a real key. Yeah.
With a weak entity, you can have partial key, and then you can have regular attributes, right?
With a weak entity, you can have a partial key, and you can have other additional regular attributes, yes.
Those wouldn't have to be got dashed in their life.
No, they don't all have to be part of the partial key. So, try not to think about tables, at least for the project, yet. Just try to get a correct ER diagram. Then we can reduce it to tables correctly later. Okay, so kind of wrapping up some more ER diagram stuff. We talked about is-a hierarchies in ER diagrams, but we haven't talked about how to translate this into tables. So here's the example we used where every employee has an SSN and a name, and then salaried employees versus hourly employees additionally have some specific attributes. So how do we translate this into tables? The basic algorithm for translating ER diagram is every entity set becomes a relation. So maybe let's just try that. So that's our first method. Every every entity set becomes its own table. So the base class, or the one at the top, gets its own table just with its attributes. And then the inheriting classes, or the derived entity sets, they get their own tables, but they have to have some way of tying themselves to the SSN and the name. Or sorry, to like the name and whatever else it is that all employees have in the base entity set. So we just pull down the primary key from the base type and add that as a foreign key pointing to the table on the top. Okay. The other, and this is a valid way to do it, there's another method to do it, and which method you pick kind of depends. We'll see where it matters. Method 2 is you don't make a table for the base type at all. You just copy all of its attributes into the derived types. So hourly employee just gets SSN and name, salary employee gets SSN and name. So it kind of looks a little wasteful in some sense, but there's kind of an important meaning here. I've been relating this stuff to like programming languages and programming concepts. What does this kind of mean in the sense of inheritance in a programming language? If we did it this way, what would that mean? Say that again? Redundant fields, okay. So maybe we do have some redundant fields here, but what does the inheritance hierarchy sort of mean here? Was there a hand over here?
Would this one be like an interface? Or would it be
So so the top thing, what this basically means is something of type just employee cannot exist. So it's like you said an interface. It's like an abstract class or an abstract type, where we can't instantiate just a plain old employee. It has to be either an hourly employee or a salaried employee. If we created a table for just employees, then we could create an employee that has no category, has no way of getting paid.
When we do this, aren't we allowing for employees now to have the same social security number but different names in each table?
So are we now allowing for employees to have the same SSN and different names in these two different tables?
Yeah.
Yes. So there are other kind of refinements we have to do in order to prevent weird stuff like that.
Yeah, the other thing I would wonder about is, couldn't you
Yeah, so what if, yeah, you might want the SSN to appear in both of these tables, and you would want the names to be the same. So here's kind of how we make this decision. If the base type is abstract, then this argues for using method 2, where we just make a table for all of the derived types. If you can have an employee that is both of these things at the same time, so maybe in this example that doesn't make sense, salaried and hourly at the same time, but you could imagine something where you want one entity to have both of these properties, then that argues for using method 1, where we do create a table for the base type, so that we don't have this problem of the same SSN showing up in the 2 bottom tables but with different names or something like that. This way we get referential integrity. We point to some other record that defines the one entity. Yeah.
So the foreign keys represent the relationships?
The foreign keys represent relationships. Yeah, it's kind of a, yeah, that's a basic way to put it. That's generally true. Yeah. Okay. So switching gears now. We're gonna get, so we've formally discussed ways to design databases in still pretty in abstract ways. We have these entity relationship models, and we have the notion of relations and schemas. So let's dive into how we're actually going to be implementing this using SQL. But so let's kind of think about how all of this stuff came to be. So back in the 70s, I mean, the time frame is really long, and you know, some of the stuff goes back to the 60s or even earlier. But the 70s is when commercial database systems kind of really started taking off. People started selling them to enterprises and businesses and stuff. But they all kind of just invented their own thing with their own language, their own. Some of them were even just like programming languages on top of like a file on the disk. Problem was, like, if you bought one solution from, say, IBM or whatever, then you're tied to that solution. So it was impractical. There were just too many of them out there. And then the relational model came along. So back in the 70s, there was this paper published about like the relational model and how we think about data in that way. And shortly after, so there were a lot of languages trying to implement the relational model. SQL was one of them. So it was one of the first to implement that. And so that stands for Structured Query Language. And remember, the relational model is dealing with structured data. So it's a language for querying structured data. Okay. And for whatever reason, SQL is the one that really took off. So ANSI standardized it in 1986. So SQL was kind of just this thing that some organization made, and then it got so popular that the Standards Institute had to get involved and say, this is the definition of SQL. It's been revised many times, as recently as 2016, so it's had a really long run, and it still is very popular today. Okay. Now, much more recently, like in the social media era, when the internet kind of really started to explode, a lot of new entrants to the data storage and database management system came into play, and they're mostly non-relational databases. So anyone heard of like MongoDB or Firebase? Yeah, like they're pretty popular. NoSQL is kind of a buzzword. NoSQL is not a specific thing, it's just a term. So Oracle NoSQL is a form of NoSQL, meaning basically it's not SQL, or like it's not a relational database. And these kind of solve certain problems that a relational database has a hard time dealing with. Specifically, like one of the things they address is distributing the data and scaling it out to like massively scaled computing power that's spread across the world or the country. Okay, but SQL is still widely used and huge. We will talk about some of these closer to the end of the semester and like the important problems that they are trying to address. Okay, so clarification between, so what is SQL? It's standardized, meaning it's just the language, and it's a standard language, just like C or C++. But C is not an implementation. C is just any old language, and then you need a compiler, and you need a set of standard libraries to make the implementation. SQL is the language. The DBMS is the implementation of the language. So C++, the analogy is C++ and GNU and C++. So there are a lot of implementations of SQL. We will be using MySQL. There's also Postgres. SQL Server is Microsoft's solution. Oracle has one. So there are a lot of them. And unfortunately, they all do different things. They all, despite the language being standard, they all kind of still treat it a little differently. It's really annoying. But we're pretty much going to focus on the way MySQL does things. You might see SQL queries that look weird because we've never seen them before because they don't work in MySQL. Okay. Now, SQL versus SQL. Probably all heard it pronounced SQL. Here's how that happened. It was actually originally called Structured English Query Language. So they pulled out SQL, they pulled out those letters to make their kind of abbreviation. There was already a trademark though. Some other organization had SQL trademarked, so they changed it to just SQL, which is why I prefer the SQL pronunciation. People from Microsoft will almost always say SQL in MySQL or SQL Server. Doesn't really matter. Both are correct. You're going to usually hear me say SQL. Okay. So SQL, turns out, is actually a combination of multiple languages. And this isn't even all of them. This is just the two major ones. Data definition language and data manipulation language. It's a little weird that they're technically separated, but data definition language is basically the commands that create tables or delete tables. And then the manipulation language are the commands that select information out of those tables, query those tables, or insert or delete information from those tables. The difference between these two is not that important, and I will usually just refer to the whole thing as SQL. But it is kind of useful to separate them. The only parts we've seen so far is DDL. We've talked a little bit about how to create tables, specify keys and foreign keys and things like that. So what we've seen is this thing at the top, how to create tables. This is just a general way. You specify the name and then the columns and their properties and then table properties. But we can also delete tables with drop table. Once a table is already made, we can alter it. So like we can change a column's type, we can add a column, delete a column, lots of things that have interesting behavior. Because if you think about, say you already have a table with a bunch of data in it, and then suddenly you change one of the column's types, there's already data there. What does it mean to change its type? If it's string or something and you change it to int, how does that even work? So we'll kind of see some examples of what happens there. So what we saw originally was this thing on the top for creating tables. It's kind of a simplified form of, think of it like a regular expression. It's not really, but it's like a general expression for how do you create a table. Here's kind of a more formal, almost regular expression. And the convention here is that SQL keywords or key commands are in all caps, and then names and identifiers, variables, and stuff like that are in lowercase. Turns out SQL will accept these commands in lowercase, so I don't have to like yell at it, like create table in all caps. You can show it, you do it either way. We do it this way usually just to show what are the keywords and what aren't. Okay, so create a table, column name, type, and then square brackets here mean optional. So optionally we can specify a default value, and then optionally we can specify column constraints and table constraints. So that whole thing, column constraint, that whole thing can turn into a lot of different things. Some of them we've seen. So like not null, unique, primary key. So this actually looks a little weird. This looks different from from the way we've done it. This is a column constraint. So when I'm saying like name, varchar 50, not null, references. So this is saying you can specify a foreign key at column creation time. Except this is one of those differences in the way the language is interpreted. MySQL will accept a command where you specify a foreign key on the column, and then it will just completely ignore it. So here I am in my library database. Let's create table test. Okay, and then I'll just do something like, let's see, I'm going to have to match the type. Let's do char 14. I'm going to try to turn this into a foreign key referencing one of those other tables. So I'll do char 14 because I know that ISBN is a char 14. So I'll call it column A is a char 14, and then I will say references, titles, ISBN. Okay. It says okay. Show create table test. So it says there's column A, it's a char 14, its default is null. This is just basic stuff about table. So it's like, just kidding, you didn't get your foreign key. Like, it just completely ignores it. So as we saw, the way that we specify foreign keys is not on the column. So I would put a comma here, and then I would say foreign key, column A, references, titles, ISBN. Okay? But doing it the other way, as we saw, is valid SQL, and MySQL accepts it, but does something really stupid. So primary key, though. You can actually specify primary key on the column name. I think I misspoke last week and said you can't, just because I never do it this way. I always think of primary key as being a table property.
So why does MySQL just fly on by that and just go, sure, I will ignore the thing you told me?
Why does it do that? Good question. I would like to ask the creators of MySQL the same question. You can set certain warnings where it would tell you that there's some stuff in your command that was ignored. But basically the reason is because you can specify a foreign key in another way. So it's not like it's removing any capability of the system, it's just changing the way you have to write it. So there's a lot of stuff. When I'm showing these like regular expressions that define the language, I'm going to leave out a lot of stuff and just show parts that are interesting to us. So I'll just kind of show this, even though there's a lot more, and you'll find stuff online that shows you all that other stuff. But I'm mostly going to stick to just like what's useful for us. Okay. So, and then let me go back to this general expression. So you can have column constraints, and then after all of your columns, you can have table constraints. So that whole thing turns into one of a lot of potentially different things. So table constraint turns into like unique, primary key, foreign key, and then up at the top in square brackets, we can say constraint and then give it a name. Turns out every one of these constraints does have a name. If we leave it off, it'll just make one up. So if we want it to be more meaningful, we can specify. And that name is important. Like if we wanted to remove a constraint, we do it by name. So we would need to know what the name is, which we can get. But if it's some random string of characters, like it's kind of harder to deal with. All right, so we've seen creating tables. We've done that a bit. I'll just leave you with the more complete reference to the expression for creating tables. This is the basic way we just multiply. It's called a cross product. We just multiply every row times every other row and combine the schemas into one. If there are two columns with the same name in the schemas, then we have to be specific about which is which. And speaking of that, two columns with the same name in both of these tables is exactly what we want. This is how we relate information between tables. So wherever those two things match up are basically the rows in this new relation that make any sense. So this is saying A's phone number is X and B's phone number is Z. Because we use the card number to match the rows, wherever those match, that's where we have real information in some sense. Is that a question? Okay. Questions? All right. So the way we do this in SQL is just called a join. So phones join patrons produces that cross product like this. So kind of just back to SQL, select everything from patrons join phones. We get a whole bunch of mostly useless information, but every once in a while there's a row where the two card numbers match. And those are the ones that are tied together. If I wanted to just show one of these card num columns, let's say I do this, select card num from patrons join phones. It says ambiguous. It doesn't know which card num I'm asking for. So I select patrons dot card num. You have to spell it right though. And then I just get the card num. If I wanted the other columns, I can do comma, name, comma, num, or whatever. Okay. Questions so far? Now again, I know some of you have seen this in my 3500 class. This is another instance of just be patient. We'll get through to more interesting stuff soon. But a lot of people here have not seen this, so bear with us. Okay. So this gets back to your original question. Comma separated table list in a select query. If you just say phones comma patrons is the same as phones join patrons. So if I did phones comma patrons comma titles or whatever, it would join all three of those tables together. Yeah.
Doesn't the performance of that get progressively worse?
So doesn't the performance get progressively worse? It gets, yes, the more joins you have, the more expensive it is. Yep.
So this simple join keyword in MySQL implies inner join or left join.
Right, so there's another way to write this. Phones inner join patrons. So join is short for inner join, and comma is short for both. So all three of these things are identical. So it turns out there's inner join versus outer join, left join, right join. There are different kinds of joins that we'll get to later, but for now, basically, this just means full cross product. Okay. So back to this idea where select is operating on one relation. So I'm saying select something from, and then I put in this list of relations, or a whole bunch of join relations. But the result of any join or multiple joins is one new relation. And then I can select stuff out of that temporary relation. Okay, and then where this starts getting useful is when we start applying filters to it. So I don't actually ever want to ask the database for this information. I would ask for this, and then I would filter some stuff out of it. So select something from whatever, join whatever, where, and then I can specify a condition. This is just a Boolean expression. So I can use standard like operators, greater than, less than, not equal, things like that. I can use and, or, not, kind of like a normal programming language. Okay, but where this gets useful is, so remember, a joined table is one relation. Two joined tables results in one new temporary table. And it has two card num columns. Like if I join patrons and phones, I have two card num columns. They're different. And I can say the ones I want are where they are equal. So just kind of going back to select star from patrons join phones where patrons.cardnum equals phones.cardnum. This automatically filters out from, remember, the full cross product. It automatically filters out just the rows where the two card nums match. This is now useful information. Now I have combined a person's name with their phone number. If I wanted to, I could remove one of these card num columns since they're obviously going to be duplicate, since that's exactly what I specified with my where filter. It's guaranteed that these two columns are going to be duplicates, so you really only would want one of them. You can easily just, instead of select star, just select one. Okay. Any questions on that? Yeah.
Is this the same as if you were to do
Join on is kind of another way of specifying the join filter criteria. Yes, so this is equivalent to saying patrons join phones on cardnum equals cardnum. Yeah. Okay, let's take a short break and then look at some more advanced stuff. So these conditions, we can build up basically a complex Boolean expression. Lots of operators, we can combine them with and or. So let's say, here's my query that finds people's names and relates them to their phone numbers. What if I just want the phone number for Joe? So I just say and name equals Joe. And strings go in quotes like that. So that gives me the name and phone number of Joe. Or I could do and patrons.cardnum greater than 2 or something like that. Okay, so yep, pretty much saw that. Okay, so this question of join on, this is kind of just another way of specifying how you want to filter the join, and it's usually based on two columns being the same. So like you're using a foreign key or a reference column. So like table 1 join table 2 on some condition is equivalent to saying table 1 join table 2 where some condition. On is less useful because it applies only specifically to joins like this. We can use where in just like select star from table where X. Okay, so kind of just slides showing pretty much what we've seen in the terminal. So I would usually use this one on the bottom, the where syntax, and I also usually won't use commas for joins. I will write the full thing out like table 1 join table 2 where whatever. Question?
So I know that in 3500 you have
Yeah.
that just use the forwarding primary key.
So natural join was the question. We'll get to natural join in a couple minutes. New lines are very useful when writing a really long or complex query, or especially when your font is really big, like on a projector. You can press enter and just move down to the next line and just terminate it by a semicolon. Okay, natural join. So it's very common to do something like, I want this table joined with this table where the two columns that they have in common are equal. And so they make a shortcut for that called a natural join. And basically what it does is it finds the columns that are in common between the two tables and then says all the tuples have to match in those columns. So it's usually one column, but it will work if you have like multiple columns in common. So let me take out this whole where clause and just do natural join. Yeah. 1.7 seconds for some reason. Okay, 0 seconds. So this just automatically figures out, okay, they both have something called card num. I will only return tuples where those two match. And notice that it automatically filtered out down to just one of those columns because it knows they're the same. It doesn't need to print both of them. So that's just a shortcut for doing that. And we'll use it a lot because natural joining tables in the natural way is the most common thing you would want to do. Okay, so query for getting the card num, phone numbers, and name for Dan. So we already actually kind of did that. Let me just press up. So in an SQL terminal, you can press up to get back to commands. So here's, like I did it for Joe. I can change this to do it for Dan. So this is select star. I think it said we want card num, name, and phone number. So I can change this to be natural join. And then just take out the card num equals card num part of the filter. I still need where. Okay, so it gives me the phone numbers card and card number. Question?
So when you're joining tables, because like I know that you specify the foreign keys that reference other tables. Is that foreign key being used for like that?
So when you specify a foreign key that references another table, is it being used to what?
Like I'm wondering what the purpose of even doing that is, other than just for saying this references this table. Like does SQL actually use that?
So the reason for foreign keys, the main reason is to define the data. So if I say that there is a foreign key on some column, it will not let me insert a row into that table where the foreign key does not exist in the referenced table. It's an integrity constraint. SQL will prevent me from doing anything weird with the tables if I specify a foreign key. But yes, they are also involved in performance optimizations when doing queries. Okay. So let's work out a query to get the titles of the first 3 books in the inventory, where assuming that books are added in order of serial number. Okay, so, and I want the titles. So just inventory is not enough. We will have to use that ISBN, join it with titles to get the title of the book. But we only want, in this example, we would want 1001, 1002, and 1003. So we could do select title from inventory, and then we'll just do a natural join. Natural join titles, where we could do serial less than 1004. Something's going on with the database server. I don't know what's going on. let's try that again. Select title from, lots of titles. Select title from inventory, natural join, titles, where serial is less than 1004. Okay, so it gives us the titles. But it's kind of assuming that we have serial numbers 1001, 1002, and 1003. So what I can do instead is so we have select title from inventory, natural join, titles. I can do order by serial. Okay, so that'll give me all of the books regardless of what the serial numbers are. Maybe we deleted the one with 1001. This just gives me them ordered by their serial numbers. And if I wanted just the first 3, limit it to 3. Okay. Get titles of first 3 books in inventory ordered by title. So same sort of trick. Order by title, and now you get a slightly different result. Now let's look at select star from titles. There's a book in there with the title Dune. That should be the first one alphabetically by title. But select star from inventory. Dune's ISBN is not in the inventory. It looks like it is. 719 versus 791. That's not it. That's not Dune. It just looks like it. So because of that natural join, Dune was not in the result when I ordered by titles and limited to 3. Okay. So we've been joining 2 tables together. But it's often useful to join more. So if we looked at the full library, like how would I get all of the books checked out by Joe? I'd have to go from patrons to checked out to inventory to titles. It involves 4 tables, and it's fine. We can join 4 tables together. We could use natural join, we could use some other criteria, filter them down, and get the books checked out by Joe. So patrons join checked out results in a table. Just think of it that way. That can be joined with a table. And you don't actually need to specify the parentheses here. You could rewrite these joins in any way. It would result in the same table. So let's get the titles and authors of books checked out by Joe. So we need to go from, remember the arrows I had drawn. We start here. We go to the checked out table, the inventory table, down to the titles table. So basically, we're going to just join all of them together. And let's see, what was the query asking for? Titles and authors. Title, comma, author. From. Patrons, natural join, checked out. Natural join, inventory. Natural join, titles. What did I do wrong? Yep. Okay, that gives me all of the books that are checked out. And notice I only selected title and author, so patron names are not anywhere in here. But I can still say where name equals Joe, because Joe is in there in some of those temporary tables before I've trimmed it down to just title and author. Okay. Query to get the phone number of the person holding Harry Potter. So it's like they haven't returned it yet. We need to contact them to tell them to return it. So it's going to be a similar thing. I'm going to just reuse most of this command because it has all this natural, all these tables joined. But now we actually have to also include natural join phones. So this is involving all the tables now, where title equals Harry Potter. Oh, except I want phone number. So now I can call that person up and say, hey, return your book. Yep.
So when you do all those natural joins, does SQL perform the cross products on all those tables? And
So
then
when I do
take
all these natural joins, does SQL do the full cross product on all of them? It does if I leave off this where clause. Actually, no, these are natural joins. There's some implied where clauses here. But is it going to do like this full cross product and result in like 5 times 4 times 7 times, the size of each of these tables multiplied together? If there were no where clauses at all, then yes. But the system automatically figures out what order to do filtering and joining, and it will do the smart thing that will result in the least amount of work. Most of the time. It's usually pretty smart. So I can rewrite this query in like lots of different ways, and as long as I'm basically just doing some simple selects with filters, it's going to translate it into the fastest way to do it.
So would natural join already imply that it's joining only on the columns which are identical even field, so it's not going to pull cross join?
So natural join implies that it's only joining, it's only resulting in the values where the keys are the same, or the 2 columns are the same. But in order to figure that out, it does kind of have to look at all of them.
Right, but it's not going to pull the full cross join.
No, it will not.
Combinations that you mentioned.
It will not return the full table like to my client. No. Okay, so that's kind of querying data. That's like read-only reading data. To add, we use insert into, and then table name, and then the keyword. These should be caps. So insert into and values should be caps, because they're keywords. But I will often write them as lowercase, just because I don't like holding down shift when I type. And then if I just say values and then in parentheses, it's expecting a value for every column. So this is creating one row, and I have to specify the value for the columns in order from left to right.
What if you have a primary key auto increment?
What if you have an auto increment or some kind of default or something? So here's an example of that. So insert into titles, ISBN, Dune Herbert. If I only want to specify 1 or 2 or some of the columns, you say insert into table name and then in parentheses the columns you want to insert into, then values, then the actual values. So values outside the parentheses here is a keyword. So this is useful if there's a default or if there's auto increment. So let's add a book. So let's do like, let's add a patron. Insert into patrons. Patron's card name is auto increment. So I just want to specify the name of the patron. And then I say values and I don't know, Steve. Okay. Select star from patrons. Gives me Steve with a card number of 9. That's because I have previously, at some point in the past in messing with this database, I've added and removed a few patrons. The auto increment doesn't reset when you delete a value.
Okay, so does the insert command also edit data that's already there? Like if you wanted to change the name?
So if you want to change the data that's already there, that is coming right up on a couple slides or something. So deleting. delete from table, if you just said delete from titles, end of statement, that would delete everything there. So you usually want to say delete from table where ISBN equals whatever, or title equals whatever. Yeah.
For this, is it like if you have a foreign key, does it stop you from removing?
So if there's a foreign key pointing to the tuple you're trying to delete, that's where when you create the foreign key in the other table, that's where you can specify whether you want to prevent it from happening or not. So if the foreign key said restrict, then it would prevent me from deleting the row in the reference to table. Yeah.
So if you did do just delete from titles and it deleted every row, would that delete the table or would it just be an empty table?
So if you did delete from titles, it would just delete the rows. The schema would still be there. It would be an empty table. Yeah. If you want to delete the table, it's drop table titles. Back up.
In terms of safety, like, is there like, if actually a whole table, titles, how to undo that or how does that?
So can you undo it? No. But unless you have like a backup of the database, which you probably do. But there is a setting you can turn on that will say, if you ever try to do something that's going to result in like massive changes, it'll say like, are you sure you want to do this? Or just prevent you from doing it. Yeah, like you have to turn on editing mode in some clients in order to be able to do this. Okay, so back to a question a couple minutes ago. What if we already have a row there, and when inserted in it, we had a typo or something and got the name wrong or whatever? So update table name, set column name equals value, and then comma, column name equals value. And then you can do where. If you leave the where clause off, again, it's gonna change every single tuple in the table. So if I said set title equals Dune, and left off that last part where ISBN equals Dune's ISBN, then every book would now have the title of Dune. Okay, and then we can change attributes of the table, or change the columns in the table. So like I can add a column. So for example, like alter table titles, add publication date. And it's the same syntax as when you're specifying the column originally. You can say, you can give it the name, and then the type, and then properties like not null, for example. So let's try that. I'm going to change to a different database. I don't want to mess with the library. We're going to do some kind of weird things. So Sandbox here is another database that has no tables in it yet. Let me just create a table. Table 1. And I'll just give it A with a type of int. Okay, and then I'll just do insert into table 1 values. I'll do like 1. And then you can specify multiple rows in a single command. 2, 3. Okay. So I've got my simple little table here. So I can do like alter table, table 1. Now alter table, we can do various things here. I can change a column, I can add a column. So let's do add B. Now, I've already got 3 rows in this table. So if I add B int, what is that going to do? Like, what are the values of B for each of these 3 rows? Let's just look at it. Okay, so it gives me null. Let's add another column. Add C int not null. Now what's it going to do? Gives me zeros. Okay. What if I do alter table, table 1? So now I can change a column's type if I want. So I can do modify A, and then I will say it becomes a char of up to 2 characters. So I'm turning an int into a string. Okay, it let me do it. And it did the right thing, it just converted those ints to strings. Okay, what if I do modify A to be a date? So the thing we're trying to answer is like, we already have a relation and it has a lot of values in it and they have some meaning. And I'm doing weird things by changing types and stuff like that. So if I select now everything, oh, what did I do? I changed it back to char. Date. So the server is slowing down again for whatever reason. Well, anyway, what it would do, since I can't show you right now, is there is no valid conversion from a string to a date, at least not these strings, 1, 2, and 3. So what it does is it converts it to a date, 0, month 0, day 0, year 0. So it'll do some kind of conversion, and you as the database administrator, you just have to know, like, well, if I'm converting from some type to a new type that makes absolutely no sense, you just have to know that all of the data in those tuples is going to be meaningless. Which means you like totally screwed up the first time when you made the tables, and something went really wrong.
Can you maybe throw an error?
You could have it throw an error. You could have it throw a warning. Okay, hold on. So before you wrap up, homework 2 due Friday. Project phase 1 is due Monday, next Monday. And that's because homework 2 is pretty short. Like, it's not like I'm just throwing 2 assignments at you at once. They're both kind of short. So Friday, then Monday. Okay, see you next week.